All right, let's start talking about canopies now. So the feature element within this sub-lecture is canopies. We're going to do the same process we've been doing where we start with our strength design. We'll move into our serviceability criteria, and if we have any. We'll talk about vibration and stability criteria. I'll show you basic boring canopies and what goes into them, and then we'll look at some drawings of specific canopies I've worked on, where I can show you the process. And then Dave will go through some fancy canopies in photos and kind of give the background or our interpretation of the background of those canopies. All right, so canopy loads, in this respect, they're much more like a building. Usually they would more fall into the kind of criteria of a building than many of the things in these sub-lectures. We would have the self-weight and any superimposed dead loads. So if we're cladding it in something heavy, and then the own self-weight of the structure. There is a chance it could be an accessible canopy. Maybe it's something that people can walk on. If so, we would have live loads up there. We could have potentially live loads. Maybe if it's on a house and it's a canopy over a door, but it's also a deck, then maybe we would have 1.9 kPa or 4.8 kPa. If it is also acting as a green roof, so maybe there's soil on top of it, it can be anywhere from 2 kPa to 12 kPa for saturated soil, depending on the medium or the type of usage it is. So that's where it's really important to know what product and what the goal and the growth idea is behind that green roof. Wind is a big part of canopy designs. Actually, I'm gonna do the wind first. Wind for elements is slightly different than for the building overall. We've looked at guards where we have a freestanding wall wind load design. For roofs, which canopies are usually considered kind of in the roof subset, we have a specific graph for looking up our CPCG. Now CPCG, that CG part is our gust factor. So it's built into our criteria or into this graph. You can see here's a roof. So this is saying these are what the CPCG loads are for our roofs and where on the roof it fits. Most canopies tend to be flat or flat-ish, just enough for drainage. So this is following into our 0 to 7 degree zone. They're talking essentially flat roofs here. So we all know that our wind equation is Q, or I guess that should be P. So for wind, I'm going to change that to, this is slide 3, P equals. Our wind pressure equals our importance factor for wind, and probably this is just regular. Very rarely would it be otherwise. We have our Q, which is our 1 in 50 year wind load that we look up in our climatic data tables. CE is our exposure factor. So if this is a canopy on the 30th floor of a building, it's going to have a higher CE factor than a canopy on the lower floors. And then CPCG, we would be pulling from this, and within that is embedded the gust factor. So we have two separate cases. We have upward loads and downward loads. So we need to look at both of those, and they need to be combined with any other loads that we could have acting on it. We also need to think about, if this was a freestanding canopy, what the drag load might be on it. Because as the wind is blowing across this, it's blowing on the projected surface, but if you had something very thin, it could still be trying to pull that object along with it. So you can see here, we would be talking about what would be similar to overhangs. So this is the roof, and then we have OC, OS, and OR. So R is the interior, S is the mid-range zones, and C is the very, very small corners. O means overhang. So that's what we'd be looking at, and these are the dashed lines that we're seeing here. So we look up our CPCG from this. snow loads. So snow loads, we would be very worried about ASL, or we would be thinking about ASL snow loads in our design of our canopies quite often. So snow load, we have our importance factor, our climatic snow value, our factors for CB, which is our our roof load, or our roof factor is 0.8. CS is sliding, which is probably going to be 0. CW, which is going to be 1 for sliding and 1 for wind. And then CA, our accumulation factor, is going to be a big deal for canopies and can often highly govern them. I'm doing one right now in kind of Halliburton area, and it has a basic snow load of 2.76 in the valleys, or like for unbalanced load it's 3.3, but on the canopy it is 7.8 kPa. So it is massive snow loads due to snow on the roof falling down onto the canopy and then not being able to blow away as easily. So you can see here what is happening. So if we have a higher building with something lower, the snow falls off of this onto the low part. And here you can see our accumulation of snow right here. So you can kind of see they've done some really nice 3D diagrams of this here. So you can imagine if this is a canopy, you can see what the intent is here with this. That we're trying to figure out what this massive amount of snow is right up against our existing building. And if anyone doubts that you can have accumulated snow loads, here's just a basic little roof without any accumulated snow loads. You can imagine if there was a building right here, all of that could fill in. All right, serviceability. We would follow normal deflection criteria for the most part, remembering that serviceability deflection criteria is a very strong suggestion. It is not mandatory. It is just a suggestion. Again, strong suggestion. So, for dead and snow load together, it is the length divided by 240, but it's often a cantilever, not always. So L divided by 120. Remember in that we get to use our snow importance factor of 0.9. So usually we get to take 10% of the snow load off. For dead and wind, it would be L divided by 240, but again, often a cantilever, so L divided by 120. For these objects by themselves, again, often a cantilever, and I've got a typo in that there. Wind, snow, L divided by 180. Because they're cantilevers, this L divided by 360 would often need to be a 180, or get to be a 180, and then we would use our importance factors for snow and wind deflection criteria. So you can see some examples here. Feel free to take a look at these that kind of show what I'm talking about for the varying deflection criteria. If we have just something cantilevered, that would be the deflection criteria we're applying to it. If we have a backspan and a cantilever, we would have different deflection criteria. If we're doing a simply supported canopy that's supported on two sides, well then the deflection criteria would be using the 240 and the 360. Vibration wouldn't really be applicable unless it was something people were walking on, and even then I think you could make the arguments that it wouldn't really apply. I'm going to go back one slide, sorry. For serviceability, I said that it's a strong suggestion because people are rarely up there, and remember serviceability is two things. It's about the comfort of the people using it, and it is about protection of finishes. If we don't have any precious finishes, it is reasonable to say that we might not be concerned with deflection criteria. That said, people looking at something deflecting in a big snowstorm makes them uncomfortable. So talking with the architect, so for me talking to you, it would be important to convey what that criteria is and making sure that the owner understood as well. What other criteria might we want to think about? Well, plate steel can have different strength requirements. And for very rough sizing guidelines, the thickness of plate would probably be the thickness would be the length divided by 100. So that would be the unsupported length of it. So basic free body diagrams. These are the supported conditions I showed you just a minute ago. Maybe we have our cantilever moment connected into a support. Maybe we're resolving that moment with a couple because there's a backspan. Maybe there's a column here and a column here. Or maybe it's a simply supported canopy and we're not worried about cantilevers at all. All right, what are some common canopy assemblies? Well, we have wood, steel, aluminum, glass, concrete. You can have all the different things. There's not really a specific canopy assembly. Each one is its own unique creation. So I'm going to show you some canopies with drawings and kind of some backstory of ones that I've designed. And then I'll get Dave to go through and talk about some images of other canopies that we just found very interesting. Some are ones we've done, some are ones we found on the internet. So via Bloor by Architects Alliance, these were the drawings I was given by the architect. So they had a very good intent of what they wanted. They have these cables on them. Architects often add cables here, assuming that it will allow the canopy to be supported here and supported here. And so we have a simply supported element spanning from our column support to our cable support, which is then fastened back here. And for gravity loads, that is fantastic. But don't forget, wind, we have uplift we have to deal with. And if that canopy is not very heavy, when the wind blows up on the canopy, we don't get to assume there's snow load up there, and we actually reduce the dead load some. And so when we think about that, you can imagine that blowing upward and that canopy cable goes slack. It's not doing anything for us, meaning we still need a moment connection here for the canopy when there's wind blowing upwards on it. Sometimes it is helpful to say that we're using this to support snow load, but it is cantilevering out on its own for wind loads going upward. So there's a bit of a balancing act there to know what and if this cable is doing anything. So here are some diagrams of what I got from the architect. So here's my model. It turns out that the cables weren't really doing much for me. We had conditions where we had openings, so we had to span across. As you can imagine, these are probably some of the worst case conditions. I had snow load on this and snow load and wind load on this. So this is my model of the canopy. This was the snow load chart that I created. So we had a peak snow load of 4.9 kPa adjacent to the existing building. That is the length of our canopy. Remember, in Toronto, a normal snow load is 1.12 kPa, because that's our importance factor of 1 times brackets 0.9 times 0.8 times 1 times 1 times 1 plus 0.4 end bracket. That works out to 1.12. And most of Lower Toronto, if it's a flat roof with nothing on it and no higher buildings, we're going to have 1.12. But this is the range of our snow load. And this is how long it would take that snow load to taper out based on the big tall building that this canopy was on. This is the canopy adjacent to the building, and this is it at its tip. So you can see we've got a high snow load here. Rather than just apply 4.9 kPa over the entirety of the canopy, I allowed it to taper out to the end of the canopy somewhat. So we managed to get it down to 3.83 out here, which is a significant reduction in the load. And don't forget, the load out here has the biggest impact on our connection back here. So snow load was a big part of this analysis, but once we had these connected for wind load, they just worked for snow load as well as something quite reasonable. So you can see here's the design right here. We have everything at not more than 90%. And we have reactions here. So we have, we've created a couple. So as this canopy tries to bend this way, we have the top trying to flip out and the top and the bottom trying to push in. So we have created a couple with the top and the bottom of these canopies, or of these columns, because of the load on the canopies. Here's deflection due to snow. So I've picked the worst case spot right here. And so this is me reducing the snow by 0.9. Let's just see what value of deflection I had. So right there, we have 17 millimeters of deflection. We have wind dragging on this canopy, bending our columns this way, and we have less than 1 millimeter of movement of the columns in that direction, or was it this direction? Regardless, I applied load as lateral loads on these to see the impact on the columns, and we were less than 1 millimeter. Wind upward. Our worst case wind load deflection upward was very, very small. It was only 0.3 millimeters. So our upward wind load deflection right here, oh, look, it's reading it from the wrong spot. That was supposed to be reading it from here. It was actually several millimeters then, but much less than our snow load deflection. No, sorry, that was our wind in the Y direction. So that again was a lateral load. Here is our wind upward. This is the one that we'd be concerned about, and it is 11 millimeters. So the snow downward is our worst case deflection criteria. So what was the length of that canopy? I'm just going to go back. Our canopy was 2.076 millimeters long, so 2076 divided by 180, we're allowed 11.5 millimeters of deflection. So wind, we've met it. It looks like snow, we're a little bit over. But that might have been the unfactored snow load, or not reduced by 0.9. So here was the canopy in plan. We had 3 different canopy types. Here were the drawings I produced as preliminary feedback. So these weren't final production drawings. They wanted an idea of what they were showing on their drawings so that they could go to a fabricator and have them designed by the fabricator. But they wanted to be able to say reasonably what they could expect. So I talked about the maximum distance between supports, the glass panels, the snow load that would be used, and the wind uplift, and that the corner conditions governed. And then this was my feedback back to the architect, and I gave them this preliminary drawing. This is the cross-section of what I was imagining this would look like. So we had our post, we had a T-shape that would taper down and support the glass. I've listed that the plate steel would be stainless, so it has a lower strength than our normal structural grade steel. Deflection limits for snow and wind, L/90. So not our L over 180, so 22 millimeter deflection limit. So this is where we found the deflection criteria very stringent. There are no finishes that could possibly be damaged on it, and no one on it experiencing it. If there is a massive snow or wind event and things deflect just a little bit more than we would expect, people aren't too fussed about it. You expect to see that. So I talked to the client about it and talked about what a reasonable deflection would be and met that criteria. All right, here is another gem of an item by Williamson. I seem to have one of their projects in almost every lecture component. So this is a canopy that I was retained to do, being supported by a base building. The owner of this house is a builder. He's a contractor, not typically doing houses. They, as a family and their construction firm, often do things in steel stud. So they have a house design in steel stud and wood joists for the flooring. So the base building engineer, this wasn't something they wanted to take on as part of their scope, which is fine, and that is reasonable. Often that happens where the feature elements are not done by the base building engineer, which is why I kind of created my company. This canopy needed to connect to things that aren't typical kind of structure elements. And we had a unique scenario that there was an engineer designing the building, but the walls were a supplied product and the floors were a supplied product. So really everything I did needed to be approved by 3 different engineering teams as well. So what they wanted here was something that read as a very, very, very thin, crisp line of steel. So it was a flat piece of rusted steel that upturned at the edges and was supported by ribs above it. Those ribs went back and connected underneath the structure below. Now, this was the outline of the second floor, and the carport below went like this. And the canopy was going right underneath the floor of the second floor. So it had the opportunity to be supported here and to be supported back here. We also had the issue that we had to worry about drainage. So this point here needed to be the lowest point on the roof. So we couldn't put framing around in any way that would retain water back somewhere. So we needed water to be able to flow out and hit an edge and get to a drainage point. So that was a critical component on how we supported this. So the only place we had that was right here, and this was detailed to lift these elements up above this steel plate so that if water got into here, it could flow out under here and still make it to this point. So let's take a look at my loading. Self-weight. This was 1/4 inch canopy plate steel. So very thin steel, is still quite heavy. We had the structural elements that were supporting it, so those ribs. Snow load. This one, the overhang was quite short and we only had snow load. Here. Remember, all of this component is underneath the floor. It goes back underneath. So all of this could have ASL on it, but it's quite a short distance of a canopy. And it was easy enough to apply that maximum 3.2 kPa of snow over all of it. Wind load, 2.0 kPa. Wind uplift, so that was wind down, wind uplift, 2.0 kPa. So the difference between wind and snow is not great. So here's an image of my model. So here we have plate steel spanning between different supports. And what I did here was I made these angles that could be welded to this plate steel, and this would have an upturn on it. and these would cantilever. They would connect to the existing building at the existing building steel and come back and connect to the existing building back at the wall of the recessed part of the building. Here it is, kind of, my modeling software, like I've said before, isn't great for giving extruded images, but it can help a little bit. So you can see here that I modeled in the base building structural beams as well. So what's interesting is that this beam was also cantilevering, picking up this simply supported beam. So we needed to make sure that our impact on this beam right here wasn't too great. So here is a model, here is the kind of results of my model. I know this one is showing up as red, and red means we're over capacity on it. But this actually wasn't doing much structurally. It was in there for stiffness. So this got modeled twice, once without making use of that and once with making use of it for our stiffness criteria. Here is a stress analysis of the plate steel. And what's our maximum value here? Looks at we're at like 25 MPa and 25 MPa. You guys remember, steel can go up to 350 MPa. Actually, this was stainless steel, so it could go up to 212 MPa. No, this one wasn't. This one was structural steel. That was the other canopy. So this could go up to 350 MPa. Here is an analysis with the reactions back here at this support. But look at this. This one's funny. This is a reaction support for my angle elements. We would need to look at the shear diagram of this beam to get the reactions of these elements. Here is deflection under snow load of the canopy, and we can see that we've got 10 millimeters of deflection right there. Under wind uplift, we've got 5 millimeters of deflection. So with that, I talked to the client. We talked about what those deflections were and if they were comfortable with that. And 10 millimeters is less than half of an inch. So it's a very, very tiny amount of deflection under an extreme snow event. So they were very comfortable with that amount of deflection, considering there was no finishes that could be damaged on it. All right, another canopy that was plate steel. This one was for Shim Sutcliffe. This one was really cool simply because we have images of it built. And this was kind of the precursor to the one I just showed you. Now, the one I just showed you was only like 3 feet long. I think this was like 3 meters long. So a lot bigger span. We needed some depth, but Howard and Bridget wanted this to read as a clean, crisp edge. But we used our secret weapon the same way we did on the other one. There are ribs above here that taper at the very end. So from below and even from a distance, it's very hard to see that profile has anything above it. It looks like a very clean, crisp edge. So here's my model. I had to go way, way, way back. I think I did this I think I was working on this in 2010, 2011. So I had to go way back in my models to try to find information on this one. But it's just such a great canopy that I really wanted to bring it up to show you. All right, here's an extrusion of it because we had those 2 planes of steel. Now, like I said, the extrusions on this aren't great, but this gives you an idea of it. Look at this funny bit right here. I'm going to go back to that image. That is me modeling steel embedded in these concrete peanut-shaped columns. That isn't exactly how it was built, but I wanted to model something that would allow me to extract some forces so that the people doing this concrete design, which was some other people in the Blackwood office, to design those easily. So here were the structural drawings. There was also a little low canopy between the building and this large canopy. And this is kind of just the low little drawing of that element right here. So you can see the outline of the canopy. You can see the dashed line of the dropped portion below. Let's take a look at what my loads are. So on this one, I say 1.12 kPa plus ASL shown. Well, look at this. Here's my ASL, or my accumulated snow loads. The kind of drop off onto snow loads here wasn't that great. This was also an older code where the way they calculated ASL was slightly different. What did the drawings look like? Well, at every, in that deeper part, every panel of steel had ribs that went all the way down to the base with tabs that allowed them to weld the plate steel onto our major elements, our major ribs. But all of this component would be hidden between the top plate and the bottom plate. We needed it to be able to be easy to connect together. As you went out on the canopy, this is what you would see further out in the one level plane of it, except this top rib here would eventually taper down to almost nothing at the edge of our steel plate. So here you can see that I modeled this as a taper. Here is the strength analysis of the plate, and again, we're well within the criteria of our steel. Here is our deflection under full snow. 40 millimeters of deflection. That's a lot. Now, we had a long span here. I think it was 3 meters. So I think it was around 3 meters. So 3 meters divided by 180 for a canopy. That's 16 millimeters of criteria. Well, we know that for things with no finishes, we'll cut that down even more. We'll maybe do it length divided by 90. So that would give us about 33 millimeters of deflection allowable. And we're exceeding that. So we talked to Shim Sutcliffe, and they talked to the client, and we talked about what was going to be reasonable in a major snowfall event. And the best way to quantify it or explain it was to say what would happen under a reasonable snowfall event. So, you know, maybe a once-a-year snowfall event. Under a once-a-year snowfall event, 18 millimeters was something more reasonable. And you would have years where you wouldn't get that at all. And remember, this is under ASL. So when we talked to them, everyone agreed that that was a reasonable amount of deflection to see in a once-a-year event. Here it is from above, up on one of the second floors, looking at it from above. This one just truly astounds me. Look at the length of that cantilever. I love that. It's dreamy. It's beautiful. I love a good cantilever. Speaking of which, one of my projects, I need to find a way to fit in how to talk. Tommy Thompson Park. That's a great canopy. I should fit in Tommy Thompson Park.
And a great cantilever.
It has a great cantilever in it, and it's finally finished, and so some of you have probably been down there. So I was the engineer for the Tommy Thompson Park Pavilion with DTAH, and it has a fantastic cantilevered canopy on it. So you can see here where these ribs are tapered back, and you can see that it's rusting nicely. We were really concerned that Howard was going to be upset with some of this oil canning that happened when they were welding it up. But Howard was like, no, it's the real product. It's the real deal. He kind of liked it. And normally people don't think of the upper view, but Howard, being Howard, even thought about how gorgeous this upper view would be on this structure. It doesn't take away from the crisp line edge. It almost seems to emphasize that clean, crisp line here. All right, I think this is the last canopy that I'm going to talk about before Dave jumps in and does kind of going through some images. This is another old one. It's one with Architects Alliance that I did in, I want to say I did this in 2009. 2008, 2009. And this is a glass canopy, but what's really interesting about this one is we had a major structure supported on two ends, but at this end, it was supported on an existing heritage building. And at this end, we had the members came and cranked down and supported on steel below. Ooh, look right here. Look what I have right here. This is a wind uplift diagram of this canopy. Because I'm doing the design of the steel, but somebody doing the glass needs to know what loads to use as well. All right, here are some details for this. We had a few interesting things that we needed to try to detail on this. So we needed them to be able to install this moment connection in the field without welding and be able to provide drainage holes for any water that could have gotten into this. Our steel needed to be able to be supported on existing heritage masonry. We had spider clamps that were picking up our glass below. So here is the model. We, at this end, so this is where the existing church is that we were connecting to, and we modeled that as a roller condition. So we allowed that to have movement in this direction. These are supported on my structural steel that's in the ground floor. And then this is a moment connection. So here is the actual structural analysis. We had 10-inch by 6-inch HSS elements making up this structure. It all worked easily. Like, look how easily those worked. If you see something like this where everything is blue, meaning that, or at least in my structural analysis software, this means that they're all at less than 50% capacity. What do you think is governing this design? If they're all at less than 50% capacity, I guarantee you deflection is what's governing this. Here is our deflection. L divided by 360 is 31 millimeters. Our worst case deflection was 29.1 millimeters. So this just worked for deflection. So this, had we made those members smaller and still worked for strength, we wouldn't have met our deflection criteria. On this particular one, we had a team that wanted the kind of proper standard of care, or the kind of strongly suggested deflection criteria met. Here is the detailing. Look at that beautiful crisp line that we had here where they didn't want to do welding on the site, which meant that we needed to allow, if water got in here, we needed water to be able to drain out. Here is our connection where we had stubs attached to the structure below that came out, and we connected these plates to the stubs. And here is our roller detail on the existing St. James Church wall. If any of you love Christmas and Christmas movies as much as I do, what's the one with Kurt Russell in it? Kurt Russell and Goldie Hawn. They have a 1 and a 2 Christmas movie. Anyway, they film a lot of the movie kind of in and around this area, and you can see this canopy in the background, in fact. Here are the spider clips, which were not designed by us, but were connected to my structural steel. Here's an image of it. You can really see why that 30 millimeters of deflection is kind of okay. Look at the length of that. This was 11 meters long. That's a huge length to cover this walkway. There it is from a distance. All right, so another project I am doing with DTAH, it's under construction right now, kind of a hotly contested project because it is near and dear to the local population, and that's the Dufferin Grove Park renovation. This is a beloved structure that the community very much makes use of. And so this has been a highly scrutinized project, but also with very high demands by the client, which is the City of Toronto. One of the mandates was a very large canopy around much of the building. But we had existing brick and block to connect to. Brick and block with existing steel that did not match the existing drawings. So we needed to be able to install this canopy through the existing brick and block and connect it to something that was sketchy isn't the right word, but we couldn't put a lot of faith in it. We needed it to be, we needed our structure to be doing the robust part of the work. So what I imagined here is that this canopy would be fabricated off-site, brought in and as one, slotted into cored holes in this existing brick and block, and then connected to this steel column that would run and connect to a joist above and into the block, into the concrete wall below. So creating our couple. So the canopy is doing this and creating our couple, similar to that Architects Alliance one that we saw at the very beginning. I was told recently by the steel detailer that this was impossible to build. Just impossible. There was no rhyme or reason to it. They just said it was impossible to build. So my kind of, so it's also not my job to solve means and methods, which is how do you actually install this thing? How do you get it into its final finished state? That said, I can't design something that's unbuildable. So I needed to be very careful in saying that yes, it was buildable, but not tell them how to build it. Because then once I say how to build it, that opens up almost liability on me as if I was directing them how to build it. Because I could think of several ways that this could be built. But the one I had been envisioning was this coming in sections, slotted through, and then connected to this. So we did have some back and forth, and we did kind of give one or two suggestions on how they could meet this detail here, which the last I heard, the canopy is being fabricated as we speak, and some of this steel will be going in very soon. So one last one that I just want to show you because it's really cool. There are no existing pictures of it that I can find anywhere of it installed. There's one picture and it's looking up below. So this is on the 7th floor of One Bloor, done by Janet Rosenberg Studios. And this is the shape of it. When I designed it, I said, you know what, you guys are going to want to design this. You guys are going to want to fill these in eventually. I think you should assume these are infilled. And they said, nope, there's no way, we're not going to infill these. And then while it was being fabricated, they changed their mind and did in fact want to come back and infill them. Luckily, I had kind of come up with a design that made this had little impact on it, luckily. So we have a canopy on very, very thin, slender columns. So yes, we have gravity load and we have uplift, but the bigger one is our lateral loads. We're not connecting back to a big, robust building. We have this kind of stacked on spindly little columns. What I did here was actually, so what they did is they built kind of steel angle frames in sections that came to the site and then were fastened together and then had the shiny plate steel put on it and buffed to a very, very high gloss. We also didn't want to put, did we moment connect these? I can't remember. Yeah, so we had the opportunity to moment connect the bases and we moment connected these columns to the upper elements. So here were my loading criteria from my spreadsheets, and you can see here I've worked through the calculation for wind loads and wind on the column because we have wind projected on it, and we also need to worry about drag. So I had wind for gravity and uplift. snow loads, and dead loads. So this wind X and Y, those are our lateral loads. Here are the reactions of this on this structure. Here are the deflections for dead and snow. So you can see kind of what that profile looks like. I didn't pull off what the actual value was. Here is deflection under the x-axis. You can see because these are moment connected, this has to stay at a right angle, and it comes up and is a right angle here. So we actually get some benefit to that stiffness. Here is wind in the y direction. And then here is the one built image that I have of it. And didn't somebody from the construction team take this picture, Dave? Was it Derek or Jamie who took this picture?
I don't recall who took it.
I know I have one other image of somebody looking up, taking a picture, and you can see their reflection perfectly in it. So you can see the columns here, there's the opening above, where you can see the building up above. But look at that shiny polish, and I cannot find a single image anywhere. Even on Janet Rosenberg's site, there's not a single image of it, just the renderings. Okay, so now we're going to jump in to Dave talking through various canopies for photo discussions.
Welcome back. So I'm going to talk to you about canopies and kind of run through them in the same way, but I'll try and be a little more brief because I know that this has been a long lecture for you guys. So we've got a bunch of them. This is a fairly common theme. Now this one is a cast-in-place concrete canopy. You can see it appears to be a green roof, but in fact that I believe is just a cold joint with a little bit of bleed through. One nice thing about cast-in-place concrete is its ability to work in two directions. It is strong in one direction and the other at the same time. Unlike wood or steel, which are stick-built, they're only strong in one direction. And concrete can also be strong torsionally. And so in cast-in-place concrete, you can see that we can do things like this, have this big two-way cantilever to cover the space. Now, one challenge with something like this is that concrete creeps over time. We tend to think of our immediate elastic deflection, and that's easy to understand. But concrete creeps. So if when the concrete is cured and the shores come out, it then sags 20 millimeters, you can count on by 2 years from now or a year from now, that'll be 60 millimeters of sag. The long-term to short ratio is about 3. So canopies, cast-in-place concrete, sags, things like this are amazing, but you have to be very careful. This type of cast-in-place concrete doesn't have that problem, partly because it's curved, partly because it's so robust. So the challenge here is not a technical challenge. This thing is extremely robust. The challenge for this canopy would have been the formwork. Forming and pouring. We've got to pour concrete on a slope and keep it from sliding out. So you need a very, very dry, very stiff concrete. This is a canopy that Shannon did for Drew Mandel on Ava Road. The lovely, lovely project. You can see it had some of the same challenges as that concrete canopy, except that this one is not concrete. I'm going to draw a little... You haven't talked to them about this, have you, Shannon?
No, I haven't, no.
So I'm going to draw you a little free body diagram because it is worth it. Because you're going to want to do this. And it's lovely in the strategy. Strategy has legs. Oops. And it can be applied to other things. So, Drew's canopy. It's easy to understand. We've got a couple of walls like this. Canopy comes out like that. And how do we support it? What Shannon did is took a beam across like this. I'm going from memory because it's been quite some time. She took a simply supported beam across like this. So it sits on the concrete here and here, piece of cake. And then another beam that comes like this and cantilevers out. Now this can be stacked one on top of the other as a totally valid load path. But if we want things shallow, we want to keep it shallow so that the whole system isn't too deep. You break that cantilevered beam here and here. This is our symbol for a moment connection. And we put a moment connection so that the moment in this beam transfers straight through that beam. So very elegant, very simple. And then this simply gets infilled with wood joists. These ones cantilever over. Oh, actually, no, they didn't. What Shannon did then, come to think of it, is further filled in with steel. Now that I think about it, further filled in with steel so that the joists could all live in the same plane as the wood, or as the wood joist could live in the same plane as the steel and keep things fairly shallow. So, is this the only way to do it? It certainly is not. Certainly we could have, or Shannon could have, put a beam here, cantilevered it out of the wall, put another one here, cantilevered it out of the wall, infilled with wood this way. Would have been just fine, but we've got this big bending moment that we have to transfer into the wall right here, and that would be a real challenge. So other ways to do this. The other thing is that this element sticking way out here, picking up all that load, would tend to sag a lot. What this does is gets the load straight to its source or straight to its point of resistance in the most direct way. So when we're dealing with big two-way cantilevers, very often a diagonal beam is the way to make things the stiffest. And when we're mixing things up with wood and steel, it is not really a big deal to cut all those wood joists to all different lengths to fill in a steel void or a steel opening. Sorry, a triangular opening.
I'm gonna see if you drew it right.
Yeah, I was just guessing. I kind of remember. It's that one.
Oh, it was pretty close. Yeah, pretty darn close.
So Don Valley Brickworks. We're going to look at the old and the new here. We'll look at the original canopy. Look at how light this thing is, and simply bolts to a brick wall. Allowable stresses in brick are very low. Even though this clearly works, it's been there forever. We would have a great deal of trouble demonstrating that the brick is adequate to carry this canopy. It's also extremely light. I think Shannon mentioned that by our calculation, we would have something like 100 pounds a square foot or 5 kPa of snow on this canopy due to accumulated snow. Anytime we've got a high roof and a low roof, we assume all the snow blows off the high roof and accumulates on the low roof. It's obviously not the case, or this would have collapsed, but that's what the code requires us to do. So light steel canopy, light metal roof. Here's the one that is currently code compliant. Sort of just as beautiful, just as light in appearance, but you can see that it's actually much more robust. A lovely little canopy at Fort York by Tanya Bortolotto. So this one's stainless steel, cantilevers up, cantilevers. So these fixed moment bases have to withstand the wind blowing horizontally plus the weight of any snow that accumulates downwards on this. Fortunately, it doesn't have to be rigid. It's not connected to anything that would be damaged by a little bit of movement, so it can move. Big glass hung by 4 button fittings, and you can see the shadow. We introduced some X bracing just to keep things lined up with each other. This is the quadruple X canopy. Shannon forgot to fill in the name of this canopy. But I just love it for its tectonics, with these floating X's. It's a space making canopy. It doesn't actually. Oh, we've got to get Albert Campbell Square in here. That's the fabric canopy with the wood trellis underneath. No, we'll talk to MBTW and find out if they have some photos. I've got photos, but I took them, so they're lousy. This is one by Brown and Story at Massey Harris Park. So this is not a canopy. This is an outdoor space making element. It provides a little bit of shade and creates a sense of an outdoor room. Suspended from the canopy is this art piece. This must have been taken when it was under construction, because this is now complete. This kind of chain link element goes continuous from end to end. This is one of the first projects where the code recommends a limit of H/500 lateral drift, and it doesn't qualify that. That's just the recommendation in the code. And we would have designed everything to that. But I dug into it at one point to find out where that came from, and it turns out it comes from windows in their frames. That the frame typically has enough movement. The frame is connected to the structure, so the frame goes for a ride with the structure. The glazing is rigid, so it stays. So while the glazing stays, the frame is doing this, and H/500 is about making sure the glass doesn't actually slip out of the frame and break the seals. And of course, that has nothing to do with our canopy. So we designed this for what was extremely bold at the time, which was a lateral drift of 1 in 100, 1%, 5 times what the code was recommending at the time. And because of that, we were able to make our columns very slender. And you can see there's no bracing anywhere. It's just slender columns cantilevered up from this base. This is one of those, I'm going to come back to this. This is one of these projects where we have to have a very serious conversation with the owner to make them understand that once you build something like this, someone will see it as a potential for shelter. And as soon as it's seen as potential for shelter, there starts to become a conversation about how do you put shelter on it and gain enclosure. And we didn't design this for any of that. So this would have been designed for a notional live load of 1 kilonewton anywhere on it and to carry its own self weight, but the structure is extremely light and not suitable to carry a roof. But we made sure that the architect and the owner understood that, and that was fine. I'm going to tell you a different story though about Young Dundas Square, the big canopy that extends out over the stage cover. The artist told us that it would have retractable awnings on it, and that the awnings would be retracted under high winds, and therefore it didn't need to be designed for snow, did not need to be designed for high wind loads. It was to be designed for very nominal loads. We said, we hear you, but we don't think that human intervention is an adequate safeguard for life safety. We need to design this for high winds. And sure enough, within probably the first year, the retractable awning stopped working. They put up lighting trusses with stretched tarps over them. There was no way that could be removed in the event of heavy weather. So we were really glad, even though the structure is very heavy, which is unfortunate, it doesn't look as good as it could. We were very glad that we had put our foot down on that project and said, no, we have to design for full wind and full snow. Canadian Peace Bridge Plaza by Nor in Fort Erie. This is an incredibly beautiful doubly curved glue lam structure. was intended to be a lamella structure, so like a Zollinger lamella. Look it up. We don't have time to talk about it. We'll talk about it later on in the course probably. But in fact, this one wound up being governed by erectability, constructability factors, and each one of these glue lambs is continuous, and the rest of them are infill. Because of that, they have different demands on them. Because of budget constraints, we had to size according to the demand to minimize the amount of wood fiber in the project. And in the end, it winds up with this kind of extraordinarily beautiful argyle kind of pattern of light and heavy diagonal members. It was not intended in the original design, but wound up being really effective. In this project, you can see, there's only bracing in one direction. I wonder what carries the lateral loads in the other direction. But in fact, it's herringbone. So the bracing is parallel to this element here, but on the other side, it's parallel to that element. So we need bracing to resist loads in both directions, but it doesn't have to be the principal direction. It doesn't have to be parallel to longitudinal and cross axis. As long as it's two non-orthogonal axes, we're fine. So in this case, we oriented our bracing on a herringbone, and that gave it stability in both directions. This is a hanging canopy on King and Duncan. This is the one thing I want to point out here. So lots of hanging canopies around. It's not hard to imagine how this works, except that cables only work in tension. That's not a surprise. Intuitively, we know that. But what is a surprise is that where we may have 4 kilonewtons per meter squared of downward load due to snow, we do have 1 or 0.5 kPa of upward load due to wind. And so canopies have to resist the upward load as well as the downward load. What we did in this case is design the connection to the building as a moment connection, so that under upward load, this cable is assumed to go slack, or this rod is assumed to go slack, and the canopy is cantilevering out of the wall. And you say, it looks like a big canopy to cantilever out of the wall. It is, except that the net upward load is very small. So the downward load, it's not cantilevering for downward load. Under downward load, we have a big tension element. There are other strategies to do this. We have done this by ballasting the roof as well. You just make sure that there's enough load on it that it can't lift up. And that's an effective strategy.
And that the ballast is a reasonable ballast that won't be blown away in the windstorm that is also causing the uplift.
Right. So we don't ballast it with stacks of greeting cards, because they blow all over the place, right? Or fine gravel. That's also bad. Okay, here's a funny story. So this is the St. Jamestown project with McLennan, Yonko, and Miller. MJMA wanted a canopy, a big wide canopy on a single row of slender columns. And I said, we can do that. We had just done Yonge Dundas Square. We knew all about big canopies on a single row of columns. We said, sure, we'll do it. Your column is 600 millimeters diameter. That's the efficient size. And Vic Yonkall says, thanks, I like the system. It's too big. We don't want 600 millimeters. So I said, okay, let's go to the heaviest wall pipe. It's 460 millimeters diameter. How's that, Vic? I don't like that. It's too heavy. So I said, okay, let's use 300 millimeter diameter pipe, but we're going to split it and we're going to make it into a lozenge shape, which is not a lozenge, an oval shape instead. So two 300 millimeter half pipes with plates in between. And he said, well, I'm getting to be okay with the width, but now it's too deep. I'm not happy with that. And I said, okay, look, we're just going to go right to the absolute limit. If these were solid, and I was being hyperbolic at the time, I said, if they were solid, they would have to be 220 millimeters. And Vic said, great, let's make them solid. So we wrote 220 millimeters solid on our drawings. We had never seen a solid thing that big, but we wrote it on the drawings anyway. Figured that the bidders would figure it out. it got bid, it got awarded, it was under construction. We get a call from the fabricator saying, yeah, what wall thickness is this 220 millimeter diameter pipe? And we said, it's not a pipe. There's no wall thickness. It's solid. He said, yeah, I know it says solid, but it's a pipe, right? It's not solid. And we said, no, it's solid. That's what's on the drawings. It has to be solid. So he said, okay, leave it with me. I don't think he was that conciliatory. I think he was a bit grumpier than that. But he went away and came back, and they sourced surplus tank axles from a military supply yard in Georgia someplace that were 220 millimeter diameter solid, and they brought them to the site, and they built the thing. They had them laying on the site, and the erector went to pick them up with a forklift and couldn't lift them. He thought they were stuck to the ground because he tried to pick them up, and instead the forklift tipped because they were individually so heavy. But worth it. It's beautiful. Single line of very slender columns. Canopy inside. Did you do this one in Yorkdale?
No, but this is just they've seen a picture of this already with the St. James Parish Hall canopy.
Right. Yeah, so
it's
this
almost
is
the same thing, but without the loads.
Suspended glass. One thing you can see here, look how the glass looks like it's made out of plywood glass. In fact, that's what it is. It's multiple layers of glass with an interlayer, and what that does is it means that if you break the top or break the bottom, if one of them breaks, it holds together. It doesn't fall out. It doesn't fall on people and cause injury. So it's much safer than solid pieces of glass.
I just want to. You've been using the mouse over here, not here, right?
Yeah.
Okay. All right.
So beautiful canopy at Nathan Phillips Square. This was a triodetic space frame with structural steel up on little spiders, with glass on little spiders, and big steel box sections. So once you're prepared to build things up out of plate, you can have any shape you want. Shannon's lovely canopy at IQ Park. Again, this one not a roof. It's a pergola, and needs to be a pergola.
But still has a surprising amount of wind load and snow loads on it, because every one of those little verticals, as much as snow can be said to fall off, we know snow is sticky. It's got something to it. And so even though each profile might only be 1.5 inches, the amount of snow it can pick up is about 4 inches on each one. And they start to bridge over each other until you could get, with the right consistency of snow, almost a full snow canopy cover on them.
I was going to ask you that. Do you remember what the spacing that you considered to bridge over?
I think I did the same dimension on each side.
Right. It's documented, I think, in ASCE, which is the American
I'm sure I
standard.
looked it up, and I can't remember now what it was, but
Yeah.
I didn't just make it up. I researched it.
Yeah. This is one of those, this goes to duty of care. There's nothing in the Canadian code that tells us that, but there is documentation in the U.S. codes, and if we are using our duty of care, then we go to the source, somebody that provides guidance. Just because the Canadian code is silent on it doesn't mean that we don't have to consider it. This is one that I did in Bronte Park in Oakville. This is a tensile fabric canopy that's intended. You can see that it's right beside a marina, so that it was intended to evoke the sailboats that were adjacent. You don't have any other pictures of this, probably, right? There's some really interesting detailing on this particular project.
But I think if we have opportunity to do the fabric lecture,
yeah,
opportunity to talk about that. So I almost didn't want to go too much into the detail. This was more about form and what's possible, and then the detailing would be very specifically the fabric lecture. If we have time for the fabric lecture. I don't know if it's built into our...
So we'll talk about this more, but this here is what I call a floating spar. It's not actually connected to the vertical. So in a way, it's a tensegrity element. Tensegrity is when you have your compression elements floating in a web of tension elements without actually connecting to each other. And the load comes back, the membranes come back onto these troughs here, and under the trough is a harp of vertical steel cables, with the idea that in the winter, the water runs out of the trough and freezes and creates an ice wall. I'm not sure if it's effective, but it's beautiful even if it doesn't. This is another fabric canopy. This is not one of ours, is it, Shannon?
Isn't this Bermuda?
No, that's not Bermuda.
Oh, okay.
But Bermuda looks a lot like this. So a cantilevered fabric canopy. We did one very much like this, and it's
in
worth.
the next slide.
Oh, why don't we go to that? Right, this is the Bermuda one. So columns rather heavy looking. On the other hand, they were designed for hurricane loads, and this has stood up to several hurricanes now. This fabric is flat, so normally fabric is form active, meaning that it gains its strength from its form, but fabric is extremely rigid and extremely strong. This fabric is actually flat, no shape whatsoever, and has stood up to a hurricane with loads sufficiently high that I think our wind loads were 80 pounds a square foot, or about 4 kPa is a wind load. Typical canopy consideration, this is our gutter. So the gutter in this case was really nicely integrated into the canopy. This is the same project. Typical boundary condition, we need to pull the fabric tight. And so one way to pull it tight is you run a cable in a pocket. It has to be curved. And then as you tension the cable, it tensions the canopy. And if you wonder if fabric is rigid, your perception is that it's not, but that's a 200 plus pound guy standing on the fabric, and you don't see his feet, but it looks like he's standing on a plywood floor. You would not know that he's standing on fabric. Shannon, do you want to handle the takeaways?
Would you be willing to go pick up the kids, and then I can finish this and mesh the videos and post them for them?
You betcha.
Thank you. We're running late, so here, keys, mask, kids. All right. So remember, basic loading criteria for canopies. They're very similar to building loads. So most of these other feature elements we're trying to interpret and extrapolate. But canopies actually often fall within the building code elements for loads, for wind and snow. We might have to refine them and adapt them, but the basic loads are coming straight out of the building code. We tend to follow general serviceability recommendations until they become prohibitive to either the design or the cost, and then we talk about whether those criteria are realistic for our canopy. And if they're not realistic, what can we pare it back to, and what can we prepare the owner and the client for as actual deflections on a day-to-day basis, or in a once a year event sort of thing. And then we drew a bunch of free body diagrams of what some canopies look like. So you have that to kind of understand what kind of the different forms of canopies can take. So that concludes our canopy lecture. Have a great day.